let's look at the substitution method. Substitution method. Okay. So now we've been through a lot with definite intervals, and we know that we got one big key here is we got to use the antiderivative to get it done, right? Okay, but then in the end, finding the antiderivative itself is particularly a very challenging job. At some point, up to this point in your learning, let me tell you guys, human beings are only able to cover about up to maybe the most is 95% of antiderivative problems out there. Taking derivative, we can do that for any function. I'm talking about 100%. Within those rules you guys learned back in your Account 1 courses, then all of the derivative techniques, you've learned it all, and you can handle any function. Right, 100%. But when it comes to taking the indefinite interval, okay, antiderivative, that we've only been doing up to like 95%, and the rest of them we have to come up with fancy techniques like leaving it for the computer. Okay, don't know how the computer can do that, but they approximate, and then eventually they come up with functions. Okay, so it's all the human brain behind the scenes, but in the end, I'm talking about it's not any elementary kind of work. But like the other day, I brought up some problem and was searching on the internet, right? And yep. See, we couldn't find it, and even Google has to say there's no elementary function that meets our antiderivative, things like that. See, that was one of the examples that we can't find it in the EQ2. So substitution method here is just another method that helps improving your work to find antiderivative. See what I'm saying? Huh? So it's all about really a big portion of the course from now on is going to be just going to focus on how we find the antiderivative successfully. Because that will be a big part of getting that into your definite interval. Okay? And so now let's start out with a problem that I begin with here. You see, back in the days when we were doing antiderivatives, I never had a chance to introduce something like this. Let's say a 2x plus 3, right? All square because see, you got some expression inside the square, and so. This problem here, let's say it's an antiderivative problem, or in this day, we can formally call it as an indefinite interval, right? So to evaluate this indefinite interval or to find the antiderivative here, what do? Prior to this point, and I didn't show any method yet, the substitution method, I just talked about it, but I didn't get into what it is yet, right? So the only choice of getting to this here is just to foil around with that thing, right? So we go. See, think about this, 2x plus 3 right here, squared, being the same as a 2x plus 3 times a 2x plus 3. See what I'm saying, huh? And then you do the foiling, and that's making it 4x squared. You guys can do the foiling independently again, right? And then that's making it 6, so that's 12x plus 9 again, right? That's after the foiling. See what I'm saying, huh? And then you do your and so this part right here is still not the calculus work. Right? It's not the antiderivative work yet. It's just the algebra that we're beating around the world. And then now we go again when we do 4 thirds x cubed, right? We all do that then. Plus now it's going to be a 6x squared. Now it's going to be a 9x, right? Now it's going to be a plus. See. Then, so it seems like foiling got the problem solved. So there was a little while we felt like, hey, then we just live good and be happy with the foiling methods, right? But then the problem becomes worse. Think about, do you want to go foiling on something like this, like a 2x plus 3, simply just that? When you raise it to the 9th power, the dx here, right? Then at that point, I'm talking about good luck with that. See what I'm saying? Huh? Good luck with that, right? Because technically, you can still foil. But something like this, you're going to end up with like a lot of time. See what I'm saying? And we don't want to do foiling. So now we desire for something to overcome the foiling and making the process going fast. Okay, making the process go to a lot more direct and fast. That's why now I'm going to erase this part right here. Okay, and I'm going to really promote that problem again. Okay. So think about when we started with an interval like this, 2x plus 3, right? Square. Oops, I meant 9. Okay. Yeah, here. So think about it just as a brain process, as something naturally telling you, something as a natural sensor, as something telling you that, hey, why don't we just let? So think about it. This whole thing here if you just completely think of that as one big variable, see what I'm saying? Just one big variable to represent the 2x plus 9, 2x plus 3. I'm not saying anything about substitution, because I'm just thinking about, hey, think about that 2x plus 3 as one package, right? Then think about the expression here, then it looks like it's going to be the package to the 9 power. See what I'm saying? Okay? But then that idea right there is what we call the substitution. See what I mean? Right? We just think about, hey, instead of working directly with a big expression, then why don't we just pack it all in one other variable, right? That's why it's called a substitution. So we substituted the whole 2x plus 3 by a bigger variable. See what I mean? Okay? But then, if we think of things like that, and then, yeah, there's something wrong about this, because the variable that all of a sudden changed to the capital F, if we still stuck with that, right? So something is not telling the right story right here. Something telling me that we're not on the right track yet. Okay? And then if you're just really brutally doing this, and think about, I've had people doing this. Just raise that to the 10, right? The big X to the 10, and there's a 1/10 here, and then plus C. And then yes, the x here means the 2x plus 3. So you're looking at the 2x plus 3 to the 10th power and multiply with the 1/10 plus c. If we just naively going this route right here, did we get the correct answer? Well, don't just dive too quickly. How do you know it's not the correct answer? You know it? How can you tell if it's not the correct answer?
Because when you reverse it, it's not the same thing.
Right? Well, we use the precise word. What does reverse mean?
Derivative it again.
What's that?
Derivative it again.
Yeah, take the derivative again, right? When you take the derivative of this thing right here, what do you get? 10 multiplied out, right? It canceled out with that 10, so it's looking at 2x plus 3 to the 9, so let's see if I can get back to that. But is it really? Chain rule says you have to multiply by 2, right? The derivative of the inside and give me that. See what I mean? Again, the only key, the only way to check whether you have gotten your antiderivative correctly done, right, is that you take the derivative of the final answer, right? And that's what he meant by reverse, but formally reverse is not a term for that. You take the derivative of your thought to be, right, antiderivative. It's supposed, if it was the correct answer, it's supposed to land right back into this beginning one being a 2x plus 3 in parentheses raised to the 9 power. See what I mean? So something was missing. So as a matter of fact, if you're taking the reverse way, you got the extra 2, so think about right in the beginning, why don't we just divide it by a 1/2 right here, right? If we already had a 1/2 right here. See, and that's making it a 1/10 here. See, I mean 1/20, right? And then yes, 1/20 over that, and that will solve the problem. See what I'm saying? Now all of that, putting that together right here, then it starts. We need to come up with something solid. Otherwise, the way how I'm showing you guys is just like we search blindly, right? We're searching blindly. We may sort of like hit it right. I mean, the try and error with that, and that's not forward with math at all. See what I'm saying? So here's how we're doing it. I still owe you guys an explanation. And see, when you think of something still, something that still doesn't add up in the sense that we change the variable to big X, but the variable that we are taking the antiderivative here is in respect to the small x here. See what I'm saying? These are two different variables. See what I'm saying? So I've been telling you guys that the indication here has to be consistent with that, right? It cannot go, you change a different variable name and you're still integrating in respect to x. That's not good. So that's something ringing a bell right there, and I didn't get to that yet. And so now, the valid method is here. Back to your beginning problem. The 2x plus 3 to the 9th, right? The capital X and the lowercase x may cause some confusion, so why don't we call it as a u? Okay? So we're going to let u equals to x plus 3. Okay, so we have that like that. Okay? So as you're doing that, then think about it immediately. The integral sign, right? That thing right there reduced into a u to the 9th. All good, right? But now, remember, as I said earlier, if you change your integral, if you change your antiderivative to the new u, see, now tentatively it's going to be all in terms of u, right? then this d thing right here has to be also in terms of u. See what I'm saying? This dx here right now, right, needs to be changed. See what I'm saying now? To something in terms of u as well. Because see, your variable you intended. The point of substituting is that you change the variable away, try to a new variable. So you need something with a du right here. See what I'm saying now? So there's a way of doing that. Okay, so now here's how I'm doing it. I'm not completely here yet. Look back at this thing right here. We do it a lot of times. You might try to call it. This is the substitution point here, the point where you make your substitution. If u equals 2x plus 3, then you guys are familiar with this, the du dx right here. What does that mean?
J to u in respect to j to x.
Okay.
So you just derivative.
Shortcut. The last thing.
So you just derivative u.
Yes, the derivative of u.
Yeah,
Right?
u equals d.
Yeah, that's yes. That's true. That's all it. Okay. But now this is the reason why I want you guys to watch that video lecture. Particularly, I just pointed out earlier on campus that back by the end of your account 1, I've been yelling all day that you treat the du dx here simply as a notation, right? Indicating as a derivative, as a notation. See what I'm saying now? You watch that video lecture, it will give you some unlocking understanding of it. At this point, think about it. These are actually, we can also treat that as a fraction as well. See what I'm saying now? It's not only just notation, but you can also treat it as a fraction, and that's where you need to see that video to understand clearly. But the du here is called, the differential, right? The differential of u variable, and then the dx here, right, is the differential, right, of x. But the clear explanation of how this was all magically allowed it to be seen, right, to be understood, and it's okay at this point. That du dx is understood as a fraction, right? As a fraction between two differentials. And it's still not a lie that you can still take that whole thing as one symbol for the derivative. But I'm talking about a different way of viewing it. There are two differentials, the differential du and the differential dy and dx here. Okay? And the derivative will actually be exactly equal, right, to the fraction of the two differentials. So aside from being a derivative, we also can see this as a fraction between two differentials, du over dx. See what I'm saying now? Okay? So I'm just reading through that video, but make sure you guys view that video for me. Okay? So now, what's the advantage of seeing this as a fraction here? By the way, can I erase this now? So, the advantage of seeing that as a fraction is that you can, if this is now a fraction, some differential du, right? The differential du over the differential dx expression as a fraction now equals 2. That means you can rearrange it. Du equals 2 times dx. Multiply the bottom expression. Just take the dx as some expression. See what I'm saying? That okay? It has a meaning, right? But then it's now an expression that has a meaningful quantity that's so infinitesimally small change in x. And so you can further, so now that means really 2 times dx. So now you can divide both sides by 2, making it du over 2. You guys follow it? Okay? And it needs also the same as a du times the 1/2. There are so many ways of writing it now. Okay? But now here's a good thing about that. Dx now can be substituted by the 1/2 du. Okay? And you can now put that in place of the dx here. See what I'm saying there? Okay? Making your final integral here, u to the 9th times a 1/2 du. Now you have displayed. Here's what I have done. I have completely washed away the old variables, right? The old variable in terms of x here, and the d here was going to also be consistent with that, right? X and dx. Now I washed the x away completely, and I went u, right, with the du. And this is just now a coefficient. See what I'm saying there? Okay? And so in that way, I'm looking at my integral being a 1/2 u to the 9th du. Okay? And then now the work all of a sudden becomes easy. It's taking the antiderivative of that. This is going to be a 1/10 u to the 10th, right? Plus, oops, I'm lying again. 1/20 u to the 10th. Let's see. So the substitution is all in that purpose of making your integral something simpler. You see what I'm saying? Huh? Turning your integral problem into something simpler. Right? So you turn that into that. And then, but now, is this our legitimate final answer? Can that be a legitimate final answer? Just think in your natural science here. Can we take the final answer, or can any professor take your final answer as 1/20 u to the 10th plus c?
No, it just,
Yeah, why not? Just why not?
no, because it doesn't exist.
No, it exists. We
It
define
doesn't
it.
exist in the problem's original state.
That's what the problem originally stated to be in terms of x. You know what I'm saying? So you want your final antiderivative to be in terms of x. That's what it is. Okay. Okay. And so here you go. So we just bring it back what u was. That's all. So that's why you gotta always know what your substitution was. Okay. So with your substitution chosen to be u equals 2x plus 3, now you go in 1/20 times 2x plus 3, right? To the 10 plus c. You guys see what I'm saying? Huh? All right. So don't rush. Take the derivative of this for me. Take the derivative of this. Are we letting back into exactly the 2x plus 3 to the 9th power? Right? If it would be, then we got a correct answer, right? And we can go ahead and put that in a box. Okay? Otherwise, something's wrong with my work. Did you get that? Did you guys find a derivative?
Yeah, it matches.
It matches, right? So this is now the correct answer. See what I'm saying now? Okay. So at this point, what is that method? Let me just write down a general guideline for you guys here. There's not really a hard rule of how you choose a substitution. It's just, so in a way, in the process I did, right? The first thing right here is just to pick a u substitution. See what I mean? And I gotta emphasize this. There are even professors out there who grade whether the students get a wrong substitution or a right substitution. I don't go that way, okay? Either way, how I see it, and you guys should be taking this advice here. When you pick a u substitution right here, there's really no correct. There's no such thing as a correct substitution. Okay, take my word on that. So I would never grade on, hey, you picked the wrong substitution. You see what I'm saying? A substitution is just a substitution. Right? You can pick any chunk of expression and let that be a substitution. Does it matter? What matters is whether it works. Okay? So the next step in my criteria right here, after you pick a substitution, the next thing is, so there are a couple of things you guys want to ensure. You see what I'm saying now? There are a couple of things you guys want to ensure. So after you pick a substitution, and like I said, there's no correct substitution, right? Then the thing you want to check is you ask yourself this question right here. Did I completely, right? Did I completely wash away? Okay. Am I using that term? I mean, is it okay using a term like that? Okay. Did I completely throw away the old variable? Or if you're starting out with x, and the old variable is the x variable, right? I'm talking about including the dx. See what I'm saying now? Okay. Including the d expression, right? So if the old variable is the x, and I'm talking about the dx, right? dx needs to be somehow in terms of du. That's what I meant by completely wash away, right? The old variable. So check for yourself that. So if you have not completely washed away, you turn your expression, a lot of your expression into in terms of u, and then you still got stuck with the dx. There is something that's where you need to look at your work again. See what I'm saying now? And you put your u substitution in, and there's still some x remains, right? Then you didn't answer this question yet. You didn't wash away your x variable completely. See what I'm saying? Now that's the first criteria you need to check yourself again. Right? But like I said, in my teaching philosophy for this stuff right here, there's no such thing as a correct substitution. Okay? Any substitution will work. And I want you guys to explore your own creativity on that in terms of picking a substitution. And then there's another. So after you pass this question right here, right? After you have an answer, yes, you washed away completely the old variable. But the next thing is you ask yourself the next question right here. Did I make the integral easier to work with? Okay. See what I'm saying now? You guys see that in my problem right there? Okay. Easier to work with, or does it get any better? Right? Okay, so in that way, magic there, see, it went from a 2x plus 3 all in the 9th power, right? And now turning that into just a 1/2, the final integral after you did the substitution. And see, yes, I washed away completely the x variable and left everything in terms of u, right, including the du right here. And so I knew I washed away completely the x variable, so that second question got checked, right? But then the third question right here, comparing this version, this final version before taking the time derivative and the beginning version right here, did I make my integral easier to work with? That's a lot easier here. See what I'm saying now? I mean, in the beginning, if you were not allowed to do the substitutions, then good luck with foiling and good luck with all that, right? Life was just hard at that time with that problem. See what I'm saying there? Okay? And so that's another criteria for you to check for yourself. But there is no such thing as only one method, as only one way of doing the substitution. So you will arrive at the same answer, but there are multiple different ways of how you arrive at it. Okay? For this lecture right here, whatever I'm going up here, you can be also as creative as you can. Okay? And so to point out the strength to point out that this particular criteria is for you to check, to self-check yourself here. You see, as far as picking a substitution, back to that first step right here, I was saying out loud, and it's legal that way. There's no right or wrong substitution. Nobody's going to hurt you for substituting u equals 2x. You guys see what I'm saying now? It's just a substitution. You have your choice to pick any expression, right? And substitute that with a simple variable. 2x is already complicated, so you substitute that with a u, right? So your expression halfway, it's going to become, halfway completed, right? It's going to become what? From the integral, right? Over the u plus 3 but to the 9th power. You guys following? Okay? And then what do we do with the dx? See? So now make sure, so this is the point where make sure you know how to find your du correctly, right? Du dx equals 2. You guys following? Okay? Okay, so we take that derivative, right? And then now, again, as I said, we can now see this also as a fraction, right? Between two differentials, du over dx, right? And you can rearrange a fraction, making it du over 2 equals dx. You guys follow with me on that, then? Okay. So now I can substitute, right? I can substitute the dx with my du. That's why now it's going to be a du over 2, right? And that's a 1/2 u plus 3 to the 9th. Whoops. Oh yeah, it's 2 plus 3 to the 9th du, right? So see, at this point you can answer yes to your second question on those among those guidelines right there. Did I completely wash away the x variable, the old variable? Yes, I did, right? But the next question here, did I make the work easier? Did I make the integral, did I make the work any easier? Not really any easier, right? Because the point is we want to find something more direct to handle that 9th power. We're still stuck with some expression, some big expression getting to the 9th power. So the third question failed, that means what? This way right here doesn't work too well. Switch route. Switch to a different integral. That's all there is. See what I'm saying now? So now when you guys start, after the lecture 2 days, in the next couple of days, you're going to do some more practice problems. But on your own time, when you see your assignments, don't worry about you not getting it about 4 or 5 times, right? Maybe the 6th time is going to work. And sometimes 10 different substitutions, it still doesn't work. Maybe the 11th one is going to work. And then eventually when you work up and enough, you're going to start getting yourself, you're going to find yourself a way into a common routine that how you should pick a good working substitution. Okay, but all I'm saying is it a working substitution or it's a failing substitution? That's all. But there's no right or wrong. Okay. I mean, there may be people can see like this doesn't work. Okay. What else? See what I'm saying now? All right. And so in that way, now as we're getting into that and right there, then let's get to work. I'm going to leave that on the board there for you guys to see those criteria. So let me now bring up a couple examples here. It's all about we're going to evaluate the antiderivative. Yeah. Okay, part A. We've got an integral that goes 3x over the square root of right. So allow me to lead the way into this right here. And on your own time, you can look at around and find even maybe, who knows, a better substitution than the one I suggest to you. Okay? So everything I'm doing up here is just simply what I suggest. Can that make sense? Okay. So how do I suggest? Substituting u equals x squared plus 5x squared. Like I said, don't be worried about that's why you can also save yourself away from that pressure, that nervous, that anxiety about how do I choose it. How do I know to choose a good one? There's no, like I said, there's no correct one, okay? It's just, maybe if it's not good the first time, choose it again. Learning, especially learning math, a lot of time it needs patience, okay? So when you guys are on your own, don't worry too much about not getting it right the first few times. So I suggest here for this problem, u equals x squared plus 5x, right? So now after that suggestion, you guys can see, okay, so du, give me 1 second. Why don't you guys change that 3 to a 6 again? Did everybody have that change it there for me? So with this one right here, so like I said, I'm saying with this suggestion of mine, right? So I suggest with that, so from this point, something that you can do on your own right here. See, find the dudx actually. Okay. The dudx turns out what? 2x, right? Plus 5. Okay, following. So no one from calculus 1 should be surprising about this, right? And so, but now at this point, again, back the whole count 1 is all about, hey, that is a symbol for derivatives, right? Don't see that as a fraction, but now at this point, you are allowed to see it's not only a symbol for derivative, but it's a fraction between two differentials, right? So now you can rearrange the differentials as follows: du equals 2x plus 5 multiply dx. See what I'm saying now? Okay. And then you can divide both sides by the 2x plus 5 expression to come up with the du over 2x. 5. You guys follow it? And see, the art in this problem is it's called the substitution method. That means we substitute some expression away and we also substitute the dx away. That's the idea. So it's all about substituting as much as we can, right? Until we got no x left over, right? That's why you check yourself the question, did I completely wash away the old variable? Right? And so now in that way, here's how I'm seeing it. In the next step, let's put it in partially. We got the 6x plus 15, right? There was no substitution for that one, and it didn't get a substitution. Let's leave it there for now. Okay, no worry. It will. Things will look at how things can go over here. In the denominator, now we can go square root of u. You guys follow it? Okay, and then that dx right here can be substituted by du over a 2x plus 5. What do you see from this? See, it looks like we still produced out some. We have still produced out some x variables for us, right? And then there's still some x variable remains. So it seems like we didn't answer that question about did I wash away the x variable?
One third.
Yeah. But think about this one right here. You can factor out the 3 again. You guys follow it? Right? From that top here, that gives me a 2x plus 5. Right? Okay, so at first we thought we didn't wash away completely the x, but look at how it happened here. When the action really comes in. See how we can cancel that away? Okay? Because the 6 is, well, like I said, the years I was doing that, so it comes to this point right here. That's why I can kind of tell ahead to switch that number here earlier. But like I said, when you're on your own and being given a prompt, right? Try with tons of different ways, okay? And you will build your experience. And so now we're looking at a 3 over square root of u, right? Du. That's what I'm saying, no? Right. So now in terms of answering that question, did I get rid of the old variable? Did I wash away the old variable completely? Yes, I did, right? And then did I make life simpler? Did I make the math problem easier? Okay? It is. Now you can turn that into a what? 3 times u to the 1/2 power. I mean negative 1/2 power, right? With a du. You guys following? Right. And now that's making it so as a new column right here, separate column. So it's going to be a, that's making it a 1/2, so it's going to be a 6, right? U to the positive 1/2. Right? Are we good? Right? Plus c. Don't forget the plus c, because here we are doing antiderivative, right? And then so with that here, what do we have? That. Okay. We have to bring back the meaning of the u variable. So it's 6 square root of the x squared plus 5x, right? Plus c. We're done. Okay. Okay. Yes, you can quickly check your final antiderivative to ensure that it is the correct antiderivative. See what I mean? So let's look at another one. So usually, let me just suggest. I just suggest, okay? And like I said, you can still be more creative in what I suggest. But look at the one we're having. It was 6x plus 15 right, over the square root. And then there's some expression inside the square root. I suggest you check the substitution equals the whole thing inside the square root. Okay. See what I'm saying now? Okay? That's just my suggestion. And it has been working. I'm not saying 100% of times, right? There's no absolute guarantee for this. But it's been working a big amount of time for me. Not so much. Okay. So you worry about square root, right? I'll put a square here. Right. And like I said, what I suggest was just a suggestion. You can see do something now. Do what I'm saying now. So don't be too worried about, don't be too hung up about what's right and what's wrong with these things we do. Okay. But now after you wrote this down, you again allow me to suggest. Okay. Why don't I suggest for you x to the 4th plus 4? Okay. Not the whole thing though, just the x plus to the 4th plus 4. Okay. You can also, I see on your own time, you can, why don't you explore on your own time, outside of class, right? X to the 4th plus 4 all squared. You can let that equal to u as well. See what I mean? There are so many ways, and you can substitute u equals 5x cubed with that. See what I'm saying? There are so many ways of working it out. But rely on these questions I put up right here to know that you're on the right track to create a working one. Okay? Sound good? So right now, at this learning point right here, I'm suggesting u equals the x to the 4th plus 4. So now we're looking at what? Du over dx. And later on, when you get advanced enough, I can just skip that line right here. You can just write it as a du equals 4x cubed times dx. You can instead of going directly into the derivative like this, okay, or you can just write it like that. So that's where you already rearrange the two differentials. See what I'm saying now? Okay. But let me just stick with the more traditional way here. So 4x cubed, right? And then you turn that into this. And then you rearrange that, making it du over 4x cubed, right? dx. So you're going to have now, so you chose this substitution. But from that substitution, you have created for yourself a substitution for the dx. See what I'm saying? No? You have produced for yourself a substitution for dx. And so now let's put the pieces together. Okay? So you got 5x cubed. Then the one in the denominator here is going u squared. And then after that, the dx here is get substituted by a du over 4x cubed. So we still got a leftover variables, right? But it can, see, the good news is it's still gonna get canceled away. So now it's turning into a, and then 5/4, right? And now what you guys are familiar with this way of writing it? It's a 5/4 and a du over square, du over u squared. It really means, because now when you are allowing that flexibility, thinking of this differential itself here as an expression, right? Then this really means what? You put that differential over u squared, or you can rearrange this as a 5/4 times 1 over u squared. That's your main function, yes, right? And then du. So now really all of a sudden in the beginning I was saying this was a one package symbol. Now it has even more meaning than that, right? It means we're taking the antiderivative, the differential du here means it's times the green product with that. Okay? But anyway, so now you've made your integral a lot simpler. So you can rewrite it as a 5/4 u to the minus 2 power. Now you're ready for finding that antiderivative, right? It's going to be a 5, okay, negative 5/4 u to the negative 1 power plus c. So that's making it minus 5/4 times x to the 4th plus 4 to the negative 1 power.